Hello, my name is James Warland. I'm with Precision Filters Incorporated. We're here today in Orlando, Florida, beautiful Orlando, Florida, at the Shock and Vibration Exchange, the 91st one. And each year we come to this. Each year they have it. We missed a year last year like everybody, so we're happy to be back this year. And this year we're demonstrating what happens when you add a lot of cable to a shock measurement. We're taking a shock measurement with an accelerometer specifically, and different types of accelerometers, what happens to your signal. So this apparatus that we see here, this is just a way of generating a shock pulse. There's a 2-inch steel ball bearing in here. You have an accelerometer mounted on that. And on the other side of it here, there's essentially the exact same thing. So when we drop it like this, and they collide together, it creates a shock pulse going to the two accelerometers, and we end up with, on the screen here, a shock pulse. And this is what we're looking for, is a pretty much right on top of each other. So I did a little lighter here, so there's a lower one, there's a bigger one. So this is a live demo that we're doing here. So right now we have on this side we have a 350 DO2, it's an IEP type accelerometer, it has some built-in filtering to it, and on the other side we have a MEMS accelerometer. This is a DevCo 7280, which has it's a bridge type configuration. There's 4 wires running to it. In this configuration, the pulses are pretty much right on top of each other. You're doing this as there's roughly 10 feet of cable here. For shock measurements, a lot of times you're going to be a big explosion. You got to have more cable than that. That's something you have when you're adding cable to a system like this. You have to pay a lot of attention to what that's going to do to your shock pulse. You don't want to get distorted waveforms and stuff. So what we can do here with our demo is we just can separate the cable. And we can add in, for our demo we have 150 feet of cable. So we get everything hooked back up here. And then we get a different shock pulse. So what's happening here, the red trace is the 350 DO2. We're using that one for a reference. I did not add any additional cable to the red one. The blue trace is the 7280, the Endevco 7280, and that has an output resistance of, it's around 5 kiloohms. So that output resistance is acting against capacitance in all this cable. And so essentially it's forming a low-pass filter. And a low-pass filter is going to give you some delay in your pulse. That's roughly 20-25 microseconds that's shifted, and we've also lost about 20% of the amplitude to it. So we've lost a fair amount of data here with this extra cable. This is something you need to be aware of when you're designing a test system. Depending on your application or how long your cable is a big factor. That's going to determine what type of sensor you should be using. To characterize this, the product that you see here that we're using as a signal conditioner. So all the signals coming out of these sensors is going through this conditioner, and the conditioner also provides the excitation. So one of the features it has, we can inject a current into the sensor through the signal conditioner. So right from the control room, you can excite 128 channels all at once, and you can record the frequency response. So you can characterize your system right from the control room, make sure you don't have a problem that's going to affect the data quality that you're looking